friend of mine, Steve Feller, who passed away on Wednesday. I don't know if anybody in the room knew Steve or knew of him, but he's one of the giants of glass science, really. I've had many interactions with him over the years, and he is a sad loss to the community, so I'd like to dedicate this presentation to Steve. So what we're going to talk about, well, this is a presentation that I worked on with my friend and colleague UoS-SHU from Rutgers University in New York State, and we currently have pretty much what's in this presentation under review for materials today in a review paper. So anybody who's interested in low level or intermediate level radioactive waste vitrification globally, search for John McCloy on Scopus and you'll find our review paper on that, which was published last year. This is the high level variant, which is hopefully going to be published probably next year now. And it's based on this presentation that we put together. This was originally delivered at the 2023 Sunglass. I've tweaked it a bit since then, but basically it's more or less the same thing. So I'm going to take you on a whistle-stop tour around the world, looking at how everybody treats their high-level waste. Lots of friends and colleagues named here. This really is a global collaboration. Colleagues from France, USA, Japan, India, and various funding bodies supporting it as well. I am not going to read all these slides out, but very, very briefly from a historical perspective. So the very first radioactive waste that was reported, I stress the word reported, to have been produced was in Canada and France back in the 1930s. And there was all the work that was basically done by the godfathers of nuclear physics back in that era, who conceived the idea of nuclear chain reactions and so on. But we all know what that led to, the Manhattan Project and everything that came after. But we don't really want to dwell on that. First of all, what is high-level radioactive waste? Well, as I'm sure many in the room already know, IAEA even, tried to insert another letter there. IAEA defines it basically it's the waste with a high concentration of highly active, long-lived radionuclides. In terms of what we're going to do with it, or what we are doing with it rather, immobilization, because often it's in liquid form, it can be dissolved up in a nitric acid liquor, for example, immobilization, and then deep geological disposal. It would appear in this country that our political processes in selecting a deep geological repository are on a similar timescale. So hopefully we'll get there one day, but we're still going through that process. Hopefully things will be moving now. So this cartoon really kind of illustrates what's going to be done with it. I'm sure most people in the room already know this. In terms of glass as a host matrix for radioactive waste, high-level waste immobilization. So the first real research that was done on this was in the 1950s. Various efforts made in this country, particularly in Canada, also in the US and France. In this country, the very first vitrification experiments were done using what was described as natural soils. It's not really clear what that is, but if you think about what soil is, organics, clay, and sand, basically. So the inorganic fractions there, you're talking about silicates and aluminosilicates. So broadly sensible. But also silicates and aluminosilicates require high melting points, and so these were being melted at 1500 degrees C, which creates challenges for vitrification through all sorts of things like refractory corrosion, melter design, volatilization losses. At the same time, the Canadians were looking at also at aluminosilicates, nepheline cyanite, which is an aluminosilicate mineral. As an aside, it's actually a raw material for making commercial container glass. So it's a relatively well-defined material, certainly better defined than natural soil, natural to wear, for example. And then very, very shortly thereafter, Goldman et al. At MIT were the first people to have been recorded to specifically focus on borosilicate glasses. Principally being, boron was added to reduce viscosity and reduce viscosity, so you can drop the melting temperature. You can drop the melting temperature, you can reduce volatilization. That's principally why boron is added to these systems, because without it, we'd be melting hotter and we'd be losing more stuff into the off-gas system. That's what it boils down to. Again, I'm not going to read all of this out, but between the early 60s and certainly the 80s, there was a lot of development work, particularly in France. The French really pushed ahead with their nuclear program in this period. The PIVA facility was built at Marcoule, which is now synonymous with the French nuclear industry. And that was capable of vitrifying up to 200 kilos of high activity solution, which is a lot. In this country, you may have heard of the Fingal process, fixation in glass of active liquors, which then became something called the harvest process. I've forgotten what harvest stands for. And then in parallel with this, the French were also developing the so-called AVM process, which is in the cartoon top right, which basically illustrates how it's done. So the radioactive waste liquor goes into a calciner. So if anybody's ever seen cement being made, it's exactly the same process. You have a calciner on a very slight angle. Stuff goes in at this end, it's rotating, it's very hot. Because it's on a slight angle, it comes out the bottom. Of course, if you're putting a liquid in, what you're doing is boiling off all of those nitrates, and well, some of the nitrates, and all of the water. So what goes in at one end is a highly active liquor, and what comes out the other end basically looks like instant coffee. A little bit more punchy than that. That process, despite this country having developed Fingal and Harvest, that process was then sold to us in the early 80s, and so the process that we've had at Sellafield to vitrify our high-level waste is based on the French process. In parallel with that, what we know about what the USSR was doing is that they were looking at aluminophosphate-based materials. So they're the only country to really push phosphate glasses as a high-level waste host medium, and we'll see more on that later. Pretty much the rest of the world has gone down a borosilicate glass route. The Russians, aluminophosphates. Okay, I am going to skip over the US aspects, which are kind of broad introduction. But basically, what we have with radioactive waste, it breaks down into defence and legacy wastes. So, for example, a lot of the decommissioning waste at Sellafield are defence and legacy wastes. Flute is a defence and a legacy waste. We then have civil nuclear waste, which results from reprocessing operations, for example. So that waste is also at Sellafield in this country, but that results from reprocessing of civil spent nuclear fuel. Within the civil, obviously there's this nuclear fuel cycle waste, but there's also the type of waste that we hear about a lot less, which is things like research waste, hospital waste, that kind of thing. It's not got the high priority that the civil nuclear and the defence nuclear waste has, but nevertheless it remains a challenge. Okay, we've heard about this, 177 tanks at Hanford, so I'm not going to repeat all that, other than to point out, you may have heard Mew mention bismuth, and you may be thinking, where on earth does the bismuth come from in the American radioactive waste? Well, the very first process for reprocessing plutonium was the bismuth phosphate process. So that's where the bismuth is from. I'll have a drink. After the bismuth phosphate process, the Americans moved on to the so-called redox process, reduction oxidation process, and then more recently they've moved on to the process that we all know, well, many of us will know, called Purex, which is the kind of the standard processing route for spent nuclear fuel. Okay. Again, we've heard quite a bit about this, but very broadly, the American wastes at Hanford break down into LAW, low activity wastes, and HLW, high level wastes. Now, in this country, we don't have liquid low level wastes of the type that would need to be stored in deep underground tanks and require vitrification in the same way the Americans have them. And basically, the reason for this is that their low activity wastes contain very little of the really nasty radionuclides. High level wastes, they're more varied. They're often in the form of sludges and salt cakes, and they contain a lot of transition metals, iron, nickel, chromium, etc. So when you come down to Sheffield Hallam, you may, I'm not putting you on the spot, Casey, but you may hear from Casey, who's looking at the effects of certain transition metals on the viscosity of radioactive waste classes. Don't worry, Casey, I'm not putting you on the spot. Much. Yeah, so okay. Recently, Hanford has moved towards what's known as direct feed vitrification. There was originally a plan to process some of the tank wastes, essentially remove them from the tanks, process them to remove certain components, and then vitrify. Now, as anybody who's ever built a process will know, you add a process step, you add a lot of cost. And so they've moved basically towards direct feed. You take it out of the tanks, you move it across to the vitrification plant, and you vitrify all of it. And that's what they're working towards. LAW vitrification has started, not will start. So that's been a new development. There was a lot of missives went out, as you said last month. They have started operations at Hanford. Waste treatment plant, WTP, vitrifying low activity waste. Now in this country that may be, oh, well done, but starting up an entire vitrification campaign from nothing, okay, it's cost a vast amount of money. It's taken far longer than they anticipated, something we're good at in this country as well. But they're doing it, and that's really encouraging. Yeah, I'm going to skip over that as well. Move to France. So the key message for the US is things are happening. They are doing it. They're moving. It's costing a lot. It's taken a long time, but it's happening. Vitrification is underway. French wastes. Okay, a lot of the French legacy wastes were centered around molybdenum-rich, uranium-rich solutions, which came from reprocessing. They also contained strange elements like tin, for example. And this came from spent nuclear fuel in gas-cooled reactors. So this high uranium, high molybdenum waste also contains phosphorus, phosphate. So not elements that you normally associate with radioactive waste, but particularly not with vitrification. So an aluminosilicate glass was made. Now this phase separates. Okay, so you get different phases forming rich or depleted in certain elements, and that forms a phase known as powellite, which is calcium molybdate. Now fortunately, calcium molybdate is insoluble in water. If you formed an alkaline molybdate, like cesium molybdate, done, because it's water soluble. And this has been developed into glass ceramics, which are now being vitrified at La Hague since, well, about the last 10 years or so. Looking at the composition there in the middle of the page, you can see that we have It's a borosilicate glass, as we might expect. It's rich in molybdenum. It also contains substantial amounts of alumina, sodium, phosphate, and so on. But broadly speaking, it's what we might expect to see from an alkali borosilicate glass. So France probably has certainly has one of the biggest fleets of nuclear power stations in the world, actually, never mind in Europe. Anybody who may or may not be interested, go online, search for, I think it's called Grid Watch or something, but there's an app, and you can look at where this country gets, on a minute-by-minute basis, you can look at where all our energy is coming from. It'll give you a little map and it'll show you all the flows and stuff, and very often when I look at it, we're buying a bit of electricity from France. And since something like 80 to 90% of their energy grid comes from nuclear power, we're buying French nuclear power. Interestingly, so are the Germans. So we have in France we have a fleet of pressurised water reactors, 56. How many have we got running in this country? It's about 3?
1 PWR and
8, so 9. And this is uranium oxide fuel, which is then reprocessed. So we've got some combination of nitrates, which are part of the reprocessing activities that use nitric acid, alkalis, alkaline earths, chalcogenized. Now they're interesting elements for making glass. Also ceramics. They don't tend to be very soluble. They do tend to be, for example, selenium, sulfur, they tend to be quite volatile. So that's a challenge. Noble metals is another challenge. Noble metals basically don't dissolve in anything much. Ceramics, glass, you name it. They tend to form things like intermetallics, and of course, if you melt them, they're going to be more dense than the medium they're present in, so they're going to sink to the bottom of whatever you try to melt them. Anyway, I'm going to move on. So, campaign to recycle the MOC spent fuel has been initiated. Also, in terms of vitrification, so I mentioned this AVM process that started back in 1978 at Marcoule. In 2000, the French have developed CCIM, cold crucible induction melting technology, which is a very different technology, and that started up at La Hague in 2010. And excuse me, for the past 5 years or so, they've had a broad range of cold crucible and induction heated modular melters operating at La Hague. So, very impressive fleet of nuclear, but also an equally impressive investment and support of developing solutions to their nuclear problems. Okay, what about this country? Well, we're in a bit of from a vitrification perspective, we're in a bit of a slightly different situation to many other countries at the moment, and the reason is this. Our reprocessing of our spent nuclear fuel in this country it's effectively ceased. It hasn't quite ceased, it's running down, but we have 2 reprocessing facilities which were in operation at Sellafield. One was Magnox, one was Thorpe. Magnox closed 3 years ago, Thorpe closed 7 years ago. Closed doesn't quite mean closed, though. There are still things going through because they have back storage flow sheets to get through. But effectively, reprocessing in the UK has stopped. Now that doesn't mean vitrification has stopped, because we have all this stored highly active liquor that will need vitrification, and then there's so-called POCO, post-operational clean-out, basically flushing the tubes. A bit like in a pub, you flush the pipes every so often to clear out the beer from the tubes, same principle. In terms of the various stages in the UK programme, it's top right, you can read it on the screen, I don't need to read it out. But since about 1990, we've been running a vitrification plant at Sellafield, which is so-called WVP, waste vitrification plant. Lines 1 and 2 since the early 90s, and then line 3 opened about 10 years later. So, oh, and more recently the VTR, vitrification test rig. This is a full-scale inactive test rig that was built to help ensure that stuff that was being done in the real world at the VIP plant was based on solid test data. And this worked very well. So we've been essentially vitrifying different blends of these two wastes, Magnox and Thorpe, over the years, and the ratios have changed, but very roughly waste loading of something like 25 to 35 weight% in the final glass. You can see the compositions of the two glasses we have in this country. Top right, MW is the basic glass that's been used since 1990. The so-called calcium zinc glass has been developed much more recently and is now the standard glass that's used at Sellafield. Its composition includes aluminium, calcium and zinc, and anybody who's looked at the composition of the French glasses will note the similarities. So there's definitely some similarity with the French glasses by introducing those additional elements. In particular, the inclusion of those components prevents the formation of those alkali molybdate phases that I mentioned, cesium phosphomolybdate, zirconium molybdate as well. Instead you form powellite, calcium molybdate. Powellite is insoluble, alkali molybdates are not insoluble. So that's the rationale there. And again, it works very well. Okay, how are we doing for time? Okay. All right. India. Well, India's program, India is not a signatory to the Nuclear Non-Proliferation Agreement, or at least it wasn't last time I looked. I don't know. Does anybody know if they've? I don't think they're signatories. But that means that some aspects of the Indian program may appear on the face of it, and I stress the word appear, to be a little bit more, not secretive, just less clear, but there is a great deal of research being done in India, and generally speaking, there's a great deal of communication and collaboration there. But basically, in terms of their reactor technologies, you know, pressurized hot water reactors, fast breeder reactors. India has a lot of thorium, so India has invested heavily in developing thorium-based nuclear fuel cycles. I don't know exactly what stage they're at with that. If anybody does, please shout out.
They've just had an approval for thorium and HALEU mixed fuels. So
Okay.
They are pushing thorium, like annular fuel pellets for thorium reactors. So it's happening. There was a guy at Newmark that was raving about the fact that it was happening. But how far that's further along the flow sheet, I don't know.
Yeah. Great, thanks, Leighton. In terms of the waste and the waste treatment technologies, the Indians have developed dual-heated ceramic melters for vitrifying some of their wastes, and there are some key facilities. One's Tarapur, one's Kalpakam, and the other one, the name of it escapes me. Let's see if it's on here. Tarapur, Kalpakam. I think it's Narora, but they're the two main ones for vitrification are Tarapur and Kalpakam. So they've been using dual-heated ceramic melters. Now I'm using all these terms, and they've all got 3 or 4 letter acronyms. They're all different ways of making glass. They all have their own strengths, weaknesses, limitations, advantages. Dual-heated ceramic melters, one limitation they have is temperature. Okay, you can't go to the very, very high temperatures that you can with certain other melter technologies. That's not necessarily a problem. In fact, we don't want to go to ultra high temperatures if we don't have to. Why? We get more volatilization. We get more corrosion of our refractories and our lining materials. We place more burden on our off-gas system. However, being temperature limited can mean, for example, that we might be waste loading limited. If you think about what's in these wastes, often a higher temperature would give us the capability to dissolve more or design compositions that would enable us to put more of particular waste in. Anyway, Trombay, that was the other site I was trying to think of. I knew it began with a T. Trombay. Okay, so this is some, on the right-hand side of your page, this is some work that was published some time ago now, but it gives a flavour of some of the relatively weird and wacky glass compositions that the Indians have been developing. I say weird and wacky, they're not. They're actually really, really good glasses in some ways. So the IR111, sorry, I just need some water. Have we got any cold water? No, hot water is better. Yeah, so the IR111 is what you might consider to be a relatively traditional alkali borosilicate glass. And you can see that the first three oxides are sodium, boron and silica. But then we've got titanium, we've got manganese, quite a lot of it, which is somewhat unusual. But relatively low waste loading, 16%. That's not a lot. You've got to make a lot of glass to immobilize a modest amount of waste. The WTR62 is a variant on that, also contains lead oxide. Now, not many countries have studied lead oxide. Anyone hazard a guess as to why people haven't been putting lead oxide into their vitrified waste forms? Anyone? Yeah.
Well, about 10% of it's going to volatilize off.
Is it?
Yeah, well, it depends on the sort of geomelt. Well, in geomelt studies, they found about between 1 and 10% of the lead just goes up the chimney. But usually, I mean, the main reason people don't use lead is it's lead.
Yes. Yeah. I wasn't aware of that geomelt study, so I'd like to see that reference if there's a document. Great.
Essentially just seeing how much put into a geomelt and see what happens.
I'd be very interested to read that. I think your second part of your answer is probably closer to the mark in terms of why people haven't been looking at lead as an additive. Because we're terrified of lead. We're talking about high-level nuclear waste. Lead is used in... Who's got lead crystal glass at home? Anyone? If you haven't got any, maybe your family members or friends might have some. You can buy it in... Well, you could buy it in John Lewis when we had one. You can buy it on the high street. Lead crystal glass, they're about between 24 and 32% PBR. So we make consumer products out of it. And the Indians have been using it because it does confer certain advantages. Okay, there may be limitations as well, of course. And this is just me kind of going off on one, but the point I'm trying to make is that sometimes we apply non-scientific considerations where we shouldn't. And I would suggest that not looking at lead as a potential, you might want to add it to well, you probably wouldn't want to add it to a plutonium ceramic, but we're talking about high-level waste. Who cares if it's slightly toxic? You wouldn't eat uranium, Uranium is actually very, very toxic as well as being radioactive, So, right, I'll move on. Point made. The Indians are the only ones who've really looked in detail at lead, which is yet another reason why they kind of stand out in the global community for looking at stuff that nobody else has looked at before. So if you're interested in some very different directions for radioactive waste immobilization media, have a look at what the Indians have been doing. Hot water, lovely. China. Now it's more challenging to find detailed information about what's happening in China, but nevertheless the information's out there. So after reprocessing, their separated high-level waste is going to be vitrified, placed in a geological repository, which is about 0.5 kilometre deep. Granite rock site, which is the top of the two Black Arrows, which is in the Gobi Desert, I understand. There's an underground lab there, which construction started 4-ish years ago. The so-called Vitrification Plant China, VPC, which is in Sichuan province, about here, and colleagues in the room who are from China, if my arrows are not perfectly sighted, my apologies.
This is totally fine.
The VPC it's actually being built by a German company, and it's effectively the same technology as the Karlsruhe vitrification plant in Germany, the VEK plant. It's a liquid-fed, dual-heated ceramic melter, so a combination of glass frit and liquid waste are being used, as opposed to glass-forming chemicals and liquid waste, which is what the Americans use. Initially, it's going to be used for legacy defence waste, but the technology may be usable later for civil waste as well. There's a commercial reprocessing plant which should, if all went to plan, it should be coming up online this year or thereabouts, and the actinising fission products will become waste, which will be vitrified. So this is definitely an area that's growing in China. In terms of glass compositions, these are some of the glass compositions that have been published from the Chinese program. As you might imagine, alkali borosilicates, some interesting minor additions in there, things like antimony, vanadium, etc. And then on the right-hand side is the composition of some of the simulated liquors, which is the mouse pointer. Yes. Yeah, this column here is simulated liquor, and then this is another target glass composition, again an alkali borosilicate. Japan. So Japan has a fleet of light water reactors. They had at least one Magnox reactor, which was one of the few Magnox reactors that we managed to export outside the UK. They had 17 licensed to operate, with another 8 pending. Of course, with the Fukushima disaster, the Japanese nuclear program hasn't been quite what it once was. Excuse me. So, about 3,000 tonnes of the Japanese spent nuclear fuel was shipped to France, and about 4,000 tonnes came here, where it was reprocessed, and then the waste from that reprocessing was then vitrified, and the vitrified products are being, or will be, or have been, probably all combination of those, shipped back to Japan. The main Japanese site is at Tokai, and their R&D on high-level waste treatment and reprocessing really began in the 70s and continued. Since the early 2000s, that plant has focused more on R&D. They did build a melter. I'm not sure if it was ever brought fully online. And in September 2014, the JAEA, Japanese Atomic Energy Authority, announced it was closing down that facility. So there's been a lot of chopping and changing in Japan in the last 10 or 15 years. This slide is broadly in line with what I just said. So we and the French vitrified that waste that had come from Japan and been reprocessed here in France, and then the glass canisters were shipped back, or are being shipped back to Japan. In terms of the Tokai vitrification facility, TVF, that I mentioned, it officially started in the 90s, but it's kind of operated for about 10 years, 15 years, and it again was a liquid-fed, dual-heated ceramic melter. Okay, So on the right-hand side on this slide, you've got Japanese composition, again, alkali borosilicate. So you can see that for the majority of the world, there's a very similar pattern. Different melting technologies, different wastes, but broadly similar immobilization matrices. The devil's in the detail though, so if anybody has an interest in this, look at those small differences and think about why they've arisen. Why is this glass different to that one? Why do they do it this way and they do it that way? There's often a very simple answer. Very few of them involve lead though. So yeah, the Japanese waste loading roughly 25%. Very similar to many other countries as well. Russia, okay. There's a lot that isn't known in detail about the Russian program over the years, but what we do know is that in 2011, about 16% of their spent nuclear fuel was reprocessed from the Viva 440, BN600 reactors, etc. And by 2030, Rosatom hoped to close the nuclear fuel cycle. They started reprocessing in the 70s. You may have heard of the Mayak site. The Mayak site is where the vitrification plant is. It's also a little bit notorious for various happenings over the years, let's say. But in terms of their vitrification facility, so late 60s, early 70s, the lab was created, pilot scale facilities. And then in the 1980s, they started up operation of different furnaces for melting. So you can see there's a first one, a second one, a third one, a fourth one, a fifth one. Basically, they'll use a vitrification furnace until it's dead, and then build another one. So, in terms of the technology, it's a dual-heated ceramic melter, single-stage vitrification. So they're basically adding aqueous waste, phosphoric acid, which is the source of the phosphate that makes a phosphate glass, and they're just chucking it into a melter. Very, very simple, arguably quite effective. And what is produced is effectively a sodium aluminum phosphate glass, a very, very different host matrix. One of the reasons for doing this was it was believed that it could incorporate lots more sulfate, and some of the Russian wastes are rich in sulfate. So you can see here I've highlighted in yellow two glasses. The first top one is the Mayak glass, and you can see that it's the only one that's rich in phosphate. All the other countries are effectively borosilicates. So very interesting, very different. Again, look at those differences. If you're working in this field, think about why they've gone down that route and they went that way. Okay, summarise. So, vitrification of high-level waste is mature. Decades of accumulated operational experience in many different places. The wastes in each country are different. The wastes between countries are even more different. Each country has its preferred vitrification technology or technologies. Some have been developed independently, some are commercialised and sold internationally. So we've got different melting technologies, different wastes, different glasses, different waste forms in every country. Even within a country there are big differences. Generally speaking, alkali borosilicates are the host matrix, but not always. So, as I've said earlier, have a look deeper and try to understand what those differences are and why they've arisen. In terms of future prospects, some programs like the one here in the UK running down. Some will soon come online or are coming online. We've heard earlier about waste treatment plants in the US, that's ramping up. Other programs will evolve or will continue, like the French one, the Indian one, the Russian one, the Japanese one, and other programs are really growing and scheduled to grow a lot, and that's, for example, the Chinese program. Okay, thank you very much.
Thank you very much. Can I start with a question? Obviously a very detailed
each country. There's one country that, for obvious reasons, we never see discussed. In your research, have you come across anything to do with how North Korea manages their nuclear waste? Is there anything in the open literature at all?
I'll be honest, Lewis, I haven't looked simply because I assumed there would be nothing there. I'll have a look, see if we can find anything.
It'll be interesting to see if there's anything on
I
there.
think.
Has anybody else has anyone ever looked at this?
They've got so their first reactor is the Bongshan reactor, which was a Magnox design, because that was the one that was kind of illicitly exported to North Korea. So if they're going to have any kind of waste at all, it's going to be something similar to a Magnox process, because that's how they've accumulated their plutonium for their nuclear weapons program. So I think the only available information that's there is that you can infer they're going to have some kind of Magnox related wastes. But I think that's about it as far as like publicly available stuff.
Can we have a Q&A of Latham's session next time?
Oh, I say it confidently, people believe me.
Yeah, I didn't know that.
They're probably ahead of the curve and they're using lead phosphates or something like that, aren't they?
Well, I mean, to be honest, there are certain countries that they are more likely to have been able to acquire knowledge and technologies from. Asterisk. So maybe there may be links through processing technologies, melting technologies, and glass compositions with those countries. Maybe, I don't know.
That's Google AI. Google AI.
Do you have any other questions?
Thorium. So, I mean, that's an interesting one. Is there much in the literature on thorium solubility in glasses generally, or not? Maybe not. I suppose other applications with thorium optical glasses. I suppose that's the thing, isn't it?
I mean, thorium was used back in the day in the so-called Kodak glasses.
Yeah, camera lenses.
Yeah. High refractive index, high lanthanide containing glasses.
So there's probably quite a lot of good options for those, isn't there?
Yeah. The only snag would be you'd have to go very hot. I mean, those would be melted at 1500, 1550, and then if you've got anything there that's volatile, be careful.
Quite a bit of work on barium borosilicate glasses with thorium as part of the Indian.
The Indian program.
Okay.
In terms of solubility, I guess partly it would depend on what temperature you get up to. If you can melt hot enough, you can probably get quite a bit in, but if not, then I imagine it'd be of a similar order to the work that's been done on flint.
Any other questions?
What is that image?
Yeah, that's just outside the conference venue where I first delivered this with UoS-SHU in Nîmes, France.
Yeah, I remember that place. I remember going to Nîmes when I was in Montpellier. It looked familiar.
I was going to put outside John Lewis in Sheffield.
Well, let's thank Paul again. Do we fancy a quick 2-minute comfort break? Yeah? Right, okay.